So when it comes to the L link, it contains the address of left subtree, and the info is the actual data storage place. If I consider the distance from the root node to this leaf node and root node to this leaf node and root node to this leaf node, the distance is same. Then we can say this kind of tree as a complete binary tree. We are making a comparison of a root node with its child node or a children node, and then we are making its arrangement. Hello everybody, a warm welcome to one and all. Welcome to the session 1 of chapter 3 of unit 3 B.Ca semester 2 subject called data structures using C. I am Rohini TS, Department of Computer Science, Vidhyaashram First Grade College, the Temple of Excellence, MYSURU. So in this chapter 3, you will be learning regarding this binary tree. So before getting into that, as we all know that in this chapter 2 of this unit, we have studied regarding this trees, and also we got to know the different terminologies with respect to the trees. In our today's session, we are going to learn about the binary tree, and also I am discussing regarding what are the different types of binary trees we have. Let me get into the session with respect to the binary tree first. Already we know what is tree, right? So tree is what non-linear data structure that will going to have a nodes as well as edges. And here when it comes to the binary tree, it is also a tree which is a collection of 0 or more nodes and finite set of directed lines called the branches that connected the nodes. So here also we are going to have a different number of nodes. That number of nodes can be either 0 or more nodes, or it can be more than 0. So either 0 or more than 0 nodes we are going to have it. In order to make a connection or communication between that nodes, we have a branches. That directed lines will be called as what? Branches that will going to connect one node to another node. So it's an order tree in which each internal node can have maximum of 2 child nodes connected to it. So if I wanted to say a tree as a binary tree, maximum it can have only 2 children. So if it is having more than that, then it won't be considered as a binary tree. So it will be a ordered collection of tree or ordered tree in which each internal node, if it is an internal node, it will going to have a child, and this is not what external node or leaf node. This is internal in nature. So it can have a child. It can have maximum of 2, but not more than that. And a binary tree is either empty. It cannot have any nodes. I can say this as 0 or more than that. If it is more than that, then maximum it needs to be only 2 child. So it consists of a node called the root together with 2 binary trees called the left subtree and the right subtree of a root. Already you know the basic terminologies. In that I have discussed what is subtrees, right? So if any of the branches deriving from a root node, then completely that left side will be considered as left subtree. In the same way, right subtree. So in this binary tree also we have a root, which is the first topmost node of a tree is called root node. So we have a tree and it consists of 2 subtree. One is left subtree and another one is right. So then what do you mean by root here? If the tree is not empty, if I have certain nodes, then we are going to call the first node as a root node. Then what about left subtree? It is a tree which is connected to the left of a root. So just take an example here. Consider here I have a root. So all the nodes which is connected to the left side of a tree, then we are calling that as a left subtree. In the same way, right subtree is what? It is a tree which is connected to the right of the root. So if I consider this as a root, if I am connecting certain set of nodes to the right side of a root node, then we can call that as a right subtree. So here a tree in which each node has either 0, 1 or 2 subtrees will be considered as a binary tree. Maximum it can have only 2 child. So if it is having one more child, then it can't be considered as a binary tree. So it can be null or 1 or 2. Maximum 2. So here you can see the representation of a binary tree. So here we have a 3 fields and it will going to have a L-link, info and R-link. This L-link will going to hold the address of left subtree. So if I wanted to traverse or if I want to visit each node, I must know its memory address. For that reason, we have a L-link or a left subtree link, and we have a info where the actual information. So we have a 10, 20, that numbering we are going to give now. So that will going to be stored in the info, and we have a R-link. R-link will going to hold the address of this right subtree. Fine. Then what node consists of or it making of? It will going to include L-link, info and R-link. Together we can call this as a node here. So this is what the representation of a binary tree node. Next, what we have, a node in a tree consists of 3 fields. That is what L-link, info and R-link, which was I discussed in the previous slide. So when it comes to the L-link, it contains the address of left subtree, and the info is the actual data storage place, or it will going to store the data or information which needs to be manipulated. And when it comes to the R-link, that is also contains the address of right subtree. If I wanted to represent that in this physical manner, then it would look like this. So here you can see that we have a root node. Root consists of 2 parts. One is left subtree and another one is right subtree. So this L-link will going to hold the address of this left subtree, and this R-link will going to hold the address of right subtree. This is the actual info or a data. Fine. Next, here you can see one of the example. Here all these are the info or data, and here the nodes which are derived from the left side of a root, then we can call that as a left subtree. This is what left child, and this is also left child. So together I can say that as a left subtree, and we are going to use L-link in order to store the address of this left subtree. And here also I have a R-link. This will going to hold the address of this right subtree. This is also consist of right child or children. This is what the representation of binary tree. Then what are the different type of binary trees we have? It includes strict binary tree, complete binary tree, binary search tree, in short that is BST, important topic here. And we have a heap tree. We'll see each one by one. So we'll go to the first one, that is strictly binary tree or strict binary tree. If the out degree in the sense what? How many number of links are establishing from that particular node. So if the out degree of every node in a tree is either 0 or 2, then that kind of tree is said to be strictly binary tree. So that is each node can have maximum 2 children or no children. So it can be internal node or external node, but at most it must be what only 2 children it can have. For example, if I consider this example here, you can see here this is what root node. Fine. So how many nodes, or what is the out degree of this node? It can be either 0 or it can be maximum of 2. So here this is 2. Right? So if I consider this node, then the out degree of this node is what? 0. If you consider this, maximum of this out degree of this node is what? 2. So then I can say this kind of tree as a strictly binary tree. So if out degree is either 0 or 2, then only we can say that as a strictly binary tree. So it can have maximum of 2 children, or it must have a 2 children or no children. Then we can say that kind of tree as a strictly binary tree. Here also you can see one of the example. We'll see the second type, that is complete binary tree. So now we got to know what is strictly binary tree, right? So when it comes to the complete binary tree, it is a binary tree in which each leaf is at the same distance from the root, that is all the nodes have maximum 2 subtrees. So here leaf node is what? The node which do not have a children or a child. Then we call that kind of node as a leaf node. So from the root to leaf node, in all the subtree, either left or right, it needs to be same. Then I can say that as a complete binary tree. Let me write the example here. So here we have a root node that will going to have 2 children, that is left one, right one, and here I will make it as a leaf node. Okay. So if I consider the distance from the root node to this leaf node and root node to this leaf node and root node to this leaf node, the distance is same. Then we can say this kind of tree as a complete binary tree. So in which each leaf is at the same distance from the root. So here I can't have it because this is one of the leaf node that is not same distance as of the previous these three leaf node. That is what we have to have the same distance of the leaf to the root. Then we can say that kind of tree as a complete binary tree. And here next we have a binary search tree. In short, it is BST. Binary search tree is a binary tree in which for each node, consider that node as X, in the tree, elements in the left subtree are less than the info of X. So, if I consider the tree as a binary search tree, I have a root node X, there will be some value and left subtree value must be lesser than the info or X, and the elements in the right subtree should be greater or equal to the info. So root must be some value and next value should be lesser than the info. If it comes to the right subtree, then it must be greater than info or equal to info. So every node in this tree should satisfy this condition if the left subtree or right subtree exists. So we'll take one example and we'll make you understand here. Consider I have a list which contains certain elements. So here we have 100, 50, 25, 200, 220, 180, 135 and 185. So with respect to this numbers or this elements, will create a binary tree here. First what I have 100. So what is the main condition? Left subtree value must be lesser than the info. So here I have a 50 which is lesser than info. So I will keep it to the left subtree. Next what I have 25. 25 is lesser than this 50. So I will keep it to the left of this 50 node. Next we have a 200. 200 is greater than this 100. So it will comes to the right side or right subtree. Next what is the element? 220. 220 is greater than this 200. So I need to keep this to the right side. I can't take it to the left side. So it will come to the right subtree. Next what we have 180. So 180 is lesser than 200. So it needs to come for the left subtree. Next what we have 135. So 135 is lesser than the 180. So it comes to the left subtree. Next what we have 185. So 185 is greater than this 180. So it will comes to the right subtree. So whatever the elements we have, that should satisfy this condition. So we are going to have a info of X that in the left subtree should be lesser than the info of X and right subtree should be greater than the X value. Then we can say that kind of tree as a binary search tree or BST. So next what we have? Almost complete binary tree. So we know what is binary tree. That is, it can have 0 node or maximum 2 nodes. When it comes to the almost complete binary tree, a tree of depth D is an almost complete binary tree if the tree is complete up to the level D minus 1. That is, the total number of nodes at the level D minus 1 should be 2D minus 1. So here you can see the total number of nodes at level D may be equal to 2D. If it is D minus 1, then it will be equal to 2D minus 1. If it is D, then it will be equal to 2D. From the root node to leaf node, all the level must be same. It can considered as a almost complete binary tree. So if the total number of nodes at the level D, the nodes should be present only from left to right, and nodes in the almost complete binary tree can be numbered level by level from the left to right. So we are giving a numbering from left to right here. And here you can see one of the example. All the nodes from root node to this leaf node should be of same distance. If it is D minus 1, then it should be 2D minus 1. So we are finding a depth here. If I am taking a depth as D, then it must be, at last it must be 2D. Then we can say that kind of tree as a complete binary tree. Next we have one more topic, that is heap tree. When it comes to the heap tree, what it means? Heap is a special case of balanced binary tree. It is a balanced binary tree, the data structure where the root node key is compared with its children and arranged accordingly. So, we are making a comparison of a root node with its child node or a children node, and then we are making its arrangement. So, if alpha has child node beta, then key alpha should be greater than or equal to key beta. That means the root node must be greater than the child node. As the value of a parent is greater than that of child, this property generates the maximum heap. Based on this scenario, we are going to have two types. One is minimum heap and another one is maximum heap. The main criteria in the heap tree is what? The root node should have a more weightage value than its children. So, based on that scenario, we have two types. One is minimum heap and another one is maximum heap. So, when it comes to the minimum heap, where the value of root node is less than or equal to either of its children. So, it can be right or left, but it will going to be lesser than the child node. So, if you see this example, here I have a value called 10. So, if I compare this 10 with this children, that is 14 and 19, this 10 is lesser. So, the root node has a lesser value or which will going to have an equal value of its child. And if I consider this 14, this has two children, 26 and 31. Even 26 and 31 is greater than this root node. Then we are calling this kind of tree as a minimum heap tree. In the same way, we have a maximum heap tree where the value of root node is greater than or equal to its children. So, if you consider this example, 44 is the root node here, and if you consider the two children, that is 42 and 35, this will going to have a lesser value. So, I can say that root node has more weightage than of its children. So, if you consider the next example 42, it is consisting of two children, one is 33 and 31, these are lesser than the root node. Then I can say that kind of heap tree as a maximum heap tree. It's all about our today's session. I hope you all understood my today's session. In my coming session, that is last session of your data structures using C, we're going to learn about the array representation of a binary tree. By making use of array, how we are going to represent a binary tree. Along with that, I will be discussing the operations, what and all can be performed on the binary tree, along with how we are going to traverse a binary tree. That is what I will be discussing in my coming session. Let me meet you in the next session. Until that, keep learning, keep on growing. Thank you.